The standard deviation will be really useful for us once we start working with the normal curve, but it's also important to understand what standard deviation is and where it comes from. At the beginning, it's a pretty intimidating looking formula, but we're going to go through that, break it down, and make sense of it so that it's not so scary after all. Okay, there's our formula for standard deviation. Pretty scary thing to look at, I'll admit. But if we break it down one piece at a time, I think you'll see that it's not so terrible after all. The first thing we see is that symbol. That is the lowercase Greek letter sigma, and that stands for standard deviation. So here what we've got is standard deviation equals all that stuff over there on the right. That's the lowercase Greek letter sigma. Easy to remember, starts with an S. Standard deviation starts with an S. As we look across the formula, we also see that guy. Kind of looks like a U with a tail almost. That is a lowercase Greek letter mu, and that is the mean of our data set. So that's the way we're going to represent mean. Remember, sigma is standard deviation, and mu is going to represent the mean. You also see the n, that lowercase n down there. That is the number of data points that we have. And then the only other thing you can see up there is we've got this x with the little 1, x with the little 2, x with the little n. The formal way of saying that would be x subscript 1, x subscript 2, down to x subscript n. Or for short, a lot of times we'll just say x sub 1, x sub 2, instead of saying subscript. What those are our actual data points. We know we have n of them, and this is the first data point, the second data point, all the way down to the last data point. We're going to plug some numbers in here, and I think if you're not comfortable with this yet, you will be after you see us plug some numbers in. So we're given the instruction, find the standard deviation of the data set 72, 74, 91. We know right away then that 72 is our x sub 1, 74 is our x sub 2, and 91 is our x sub 3. So when we go to plug in, those are going to get plugged into the formula in those places. One of the important things in that formula was that we needed mu, the mean of our data set. So that's the first thing we should find. And that'll be 72 plus 74 plus 91, all divided by 3. That's going to be 237 divided by 3. And so the mean of this data set is 79. So let's see, I know what mu is. I know what x1, x2, and x sub 3 are. And I need the number of data points that I have. Well, that's not hard to find. That's just 3. So let's plug this into our formula and see what it looks like. I'm going to have sigma equals square root of, alright, let's see here, x sub 1 minus mu squared plus x sub 2 minus mu squared plus all the way to my last data point. Well, I only have one more, so that'll be x sub 3 minus the mean squared, all divided by the number of data points that I've got. Let's take a look at that and kind of walk through it. So I've got sigma equals first data point minus the mean squared, second data point minus the mean squared, third data point minus the mean squared. That's my last data point, so those are the only ones I need to put in. If I had more data points, I'd just keep going with that process and then divide by however many data points I have. Now let's evaluate this and figure out what the standard deviation of this set really is. Okay, here's where we left off. And now let's start cleaning it up a little bit. So sigma is going to be the square root of, alright, 72 minus 79. That'll be negative 7 squared plus 74 minus 79 will be negative 5 squared. And then 91 minus 79 will be 12 squared all over 3. You'll see that this cleans up in a hurry. And negative 7 squared will be 49. Negative 5 squared is 25. And 12 squared is 144. Still all divided by 3. I am going to slide over here to keep this on one screen. When we add those together, we've got the square root of 218 over 3. Go ahead and divide those and have square root of 72.66667. Your calculator may have more decimal points than that. Go ahead and keep them all for now. And then this step is the one that students tend to forget sometimes. This very last step, take the square root of that number. So we've got to take the square root of that number, and we find out that the standard deviation for this data set is 8.52447. We're usually going to round this to the nearest hundredth, so we find the hundredths place. Look one space to the right. 4 or lower, we're going to round down. So our final answer here for this one is that our standard deviation is 8.52. You might be thinking, okay, the formula is not as scary as I originally thought. I sure hope that's where you are. But you also might be thinking, what is this useful for anyway? I mean, it's a neat little calculation, but it tells us how spread out a data set is. Let's take a look at what I mean. We found the standard deviation of the data set 72, 74, 91. We found that that standard deviation was 8.52. The standard deviation of a different data set, 23, 27, 40, turns out to be 7.26. You can calculate that on your own for practice. It's probably a good idea. See if you can do that one. And now if the question is, which of these data sets is more spread out? Well, whichever one has the higher standard deviation, that's the one that's more spread out. So this data set right here, because it has a higher standard deviation, is more spread out than the other. Maybe this is test scores in a class and you want to see which class was more consistent. Pretty hard to tell just by looking at the raw numbers. We calculate the standard deviation and we see, well, this class had scores that were more consistent than the other because their standard deviation was lower. Really, the use of the standard deviation is going to come into play when we study the normal curve, but it does give us a way to measure how spread out a data set really is, and we can compare data sets to each other using standard deviation.